Welcome back to another deep dive. Today, we're taking on a massive, foundational pillar of modern machine learning. We are demystifying support vector machines, or SVMs. Now look, if you've ever peeked at the math behind SVMs, I get it. It can seem absolutely terrifying. You've got hyperplanes, quadratic programming, Lagrangians, the whole shebang. But beneath all those complex equations, there's actually a visual, geometric intuition that is just beautiful. Our goal for this explainer is to build that intuition right from the ground up. We'll start with simple, intuitive visuals, and then I'm going to show you exactly how that heavy math elegantly solves the problem. Okay, let's dive right into this.
Here's our roadmap for today. First, a brief history of AI. Then, drawing the optimal boundary, maximizing the margin, solving the math problem, the Lagrangian dual approach, and finally, inner products and similarity. All right, let's get started.
To really appreciate why SVMs are such a game changer, we kind of need some context. So, Section 1, a brief history of AI.
Prior to 1980, almost all machine learning methods were linear. Right? They had these really solid theoretical foundations, which is great, but they were pretty limited in what they could actually learn. Fast forward to the 1980s, and things get exciting. Decision trees and neural networks show up, and they finally allowed us to efficiently learn nonlinear decision surfaces. But there was a catch. They had very little theoretical backing, and honestly, they all suffered from a massive flaw, getting stuck in local minima. You'd run a neural network, get a decent answer, but you could literally never be sure if it was the absolute best answer. Then the 1990s roll around, and support vector machines enter the chat. They basically brought the best of both worlds. You got the efficient learning for nonlinear functions, but now it was backed by this beautiful, rigorous computational learning theory.
So you might be wondering, what is this rigorous theory actually trying to do? Let's move to Section 2, drawing the optimal boundary. Imagine a simple 2D space. Our objective is just to separate the red points from the green points. Now, think about it. There are infinite possible solutions here. You could draw literally an infinite number of dividing lines that perfectly separate that red from the green. Early neural networks? Well, they might just stop the second they find any line that works. It's essentially a bit of guesswork, really.
Which brings us to a really massive question. Which hyperplane do we actually pick? I mean, how do we decide which of those infinite lines is the truly optimal one? And maybe more importantly, which data point should actually influence that decision? If we're talking linear regression or an early neural net, every single point influences the line. But is that really necessary?
Well, this is where the magic happens. The answer is no. We absolutely don't need all the points. We only need the difficult ones. We call these the support vectors. Basically, support vectors are the critical data points that lie closest to the decision surface. They're the ones right out there on the front lines, the hardest ones to classify. Unlike other methods that use every single data point to calculate a boundary, SVMs focus almost entirely on these critical few. It's totally brilliant.
So, once we identify these critical support vectors, what exactly are we doing with them? That takes us to Section 3, maximizing the margin.
Let's use an analogy here. Imagine the dividing line is the center line of a street. We don't just want a thin, tight line. We want the widest possible street that can fit between our red and green data points without, running any of them over. The shaded area is our street. And notice this, the support vectors are the exact data points that are just barely touching the edges of the street. They are quite literally holding the margins in place.
Let's formalize this a bit. H0 is our median, the exact center of our street where the equation equals 0. Then we have H1, which is the boundary on the positive side, and H2, the boundary on the negative side. Now we define D plus as the shortest distance from the center to the closest positive point, and D minus as the shortest distance to the closest negative point. So the total margin, the full width of our street or gutter, is exactly D plus D minus. Our entire objective, the whole goal, is to make that total value as large as possible.
So here's the absolutely crucial takeaway. Moving a support vector fundamentally shifts your entire decision boundary. But moving literally any of the other data points, the ones safely chilling behind the margins, has absolutely zero effect on the boundary. None. This is what makes SVMs so incredibly efficient. The algorithm ensures that only a tiny, tiny subset of your training samples determines the final model.
Okay, we want the widest street, but computers don't understand streets. They need math. Section 4, solving the math problem.
To mathematically maximize that total margin between our classes, it turns out we actually need to minimize the length of our weight vector, which we denote as W. And because of how the geometry works out, minimizing this weight vector while ensuring all the points stay on the correct side of the street, well, that translates directly into a constrained quadratic programming problem.
And this perfectly illustrates why SVMs are such a powerhouse. Think about a 3D paraboloid. Because our objective function to minimize W is quadratic, the mathematical surface we're navigating basically looks like a giant bowl. Why does that matter? Well, a bowl has exactly one distinct bottom. There is only a single global minimum. This completely avoids that massive headache of local minima traps that plagued neural networks in the 80s. Actually, think about it this way. When an SVM finds the answer, it is mathematically guaranteed to be the optimal answer. No guessing involved.
If we look straight down into that bowl, kind of flattening it out into a contour map, we can see the intuition of constrained optimization. The ellipses are our quadratic function, trying its hardest to get to the center minimum. But we have constraints, our data points, represented by a straight line. The optimal solution is found exactly at the intersection where our function and our constraint line are perfectly tangent to each other. Right at that tangent point, their gradient vectors, those little arrows pointing outward, are perfectly parallel.
So, how do we actually calculate that algebraically? Welcome to Section 5, the Lagrangian dual approach.
The original problem, where we're trying to minimize over the weights W and the bias B, is called the primal problem. But by introducing Lagrangian multipliers, we can actually flip this into what's called the dual problem, and the shift in variables here is just incredibly clever. By substituting our equations, we brilliantly get rid of the dependence on the weight vector W and the bias B entirely. Instead, we're now maximizing over a totally new set of dual variables, denoted as alpha or just A.
Now, prepare to have your mind blown a little bit, because here is the elegant twist of the dual problem. When you take the derivatives and solve for these new A variables, you find that almost all of them just drop straight to zero. The only A variables that are strictly greater than zero correspond exactly to the support vectors. The math literally just zeroes out all those irrelevant data points we talked about earlier, leaving only the critical points sitting right on the margin of our street.
You might be wondering, why not just solve the primal problem and be done with it? Well, this brings us to Section 6, Inner Products and Similarity.
Here is the incredible payoff. Look at the dual problem equation. It allows us to compute our boundary using entirely and strictly the inner products or dot products of our data points relative to each other. We're multiplying vector x sub I by vector x sub j. And if you remember from linear algebra, an inner product is a direct measure of similarity. If two vectors are perfectly parallel, their inner product is high, meaning they're very similar. If they're perpendicular, their inner product is zero, completely dissimilar.
Let's break down how this similarity measure actually plays out inside the algorithm. The dual problem evaluates pairs of data points, right? If two data points are completely dissimilar, their inner product is zero, and the algorithm just ignores them. If two points are very similar, and they predict the same class, like let's say they're both clearly red, the algorithm actually downgrades their impact, because they don't really help define the boundary. But if two data points are incredibly similar, meaning they sit right next to each other in space, but they belong to opposite classes, boom! This maximizes the sum in our equation. The algorithm is actively hunting for the most similar data points that have conflicting labels. Those points are right on the edge. Those are your support vectors.
It really is a masterclass in elegant optimization. We've moved from just drawing a simple line to rigorously ensuring it's the absolutely perfect line, utilizing only the data points that truly matter, all mapped out by similarity. But this leads us to a massive cliffhanger. We've assumed this whole time that we can actually draw a straight, flat hyperplane to separate our data. But what happens in the real world? What happens when the data is entirely jumbled and literally cannot be separated by a straight line at all? Well, it turns out that inner product similarity trick we just learned is the exact key to unlocking nonlinear spaces using something called kernel functions. But that is a fascinating explainer for another day. Thanks so much for joining me on this deep dive.